One of you guys pointed us to this artist's page, a guy called Loris Ceccini, and he does these amazing sculptures in resin. And you asked us how we'd go about creating similar structures inside of Houdini. And at first when looking at this, I was not really sure what was going on there. However, I found different artworks on his website. This here explained a lot to me. What we're looking at here are interference patterns. How do interference patterns work? Imagine looking on a water surface. At one point, this orange point here, there's a buoy moving up and down. So it is oscillating and it's creating waves. So when you look at it from the top, you could visualize it like this. And from the side, it does something like this, those sine waves emanating from this point. If you introduce a second buoy and have it moving at the same frequency, so oscillate at the same frequency, then the waves generated by those two buoys meet. And if the buoys happen to oscillate at the right frequency and be the right distance apart, the waves meet in this special pattern here. And what they do is they add up to each other and thus cancel out each other, which is called destructive interference. If the waves meet at their peaks, they amplify each other, which is called constructive interference. And the shape of the resulting wave when two wavefronts meet depends on the distance of both oscillators and the frequency at which they oscillate. And depending on the oscillator's position and frequency, the resulting wave can be quite complex, as exemplified in this diagram here, where the orange wave is the sum of this purple and blue wave in the background. So to generate our sculptures, what we'd like to calculate is the amplitude at a given point on a grid. So the red dot here is the point that we're looking at. And let's say we have two oscillators, those are these orange points here. Now to calculate the amplitude, that means the strength on the red point, we need to know the distance to each oscillator. So we need to know how many oscillators are there in our example 2, and their individual distance to our active point. So this is the distance 1, and this is the distance 2. And also we need to know the frequency of each oscillator. And to simplify matters a bit, let's assume both oscillators swing with the same frequency. And what we can do then is plug in those values, as for example here, the distance 1, let's say it's 30, and the distance 2, in our case, let's say it's 11. We can plug this in together with the frequency, which is in our case fixed for both oscillators, and I just chose a value of 10 for our example. We can plug in those values into a simple sine function to calculate the individual strength of the waves meeting at that red point here. So the wave coming from this oscillator here is calculated with this formula up here. Strength 1 equals the sine of this distance here times the frequency, and the strength of the wave coming in from this oscillator here, that's bottom line here, is the sine of this distance here times the oscillator's frequency. So those two values we're calculating here would correspond to the blue and purple wave in this example here. And to get our final interference pattern, what we have to do is add the two values. So we will just combine the two wavefront strengths to give us our final overall strength, which will result in this interesting looking interference pattern. So to build this in Houdini, we will drop down a grid first, dive into its geo, and scale it down to be maybe 2 by 2 in size, and increase its rows and columns to say 500 by 500. And we can still increase this later, depending on the resolution and shape of our interference patterns. Also, what we'd like to do is create some points which will serve as our oscillators. In this case, I'll just gonna drop down a circle, set this to be on the ZX plane here, and dial back its radius to say 0.5, yeah, something like that. And I will just use a scatter to scatter, say, 11 points on this circle, and I will disable the relax iterations, so I have now those few points scattered in here. And each individual point will be a single oscillator. So what I'd like to do now is for each point in the grid, I would like to find all oscillators and all individual distances to each oscillator, which I will then store on each individual point in the grid. So let's drop down a point wrangle, wire up our grid in the first slot, and the scatter in the second slot. And in the point wrangle, the first thing I'd like to do is find out how many oscillators there are. And of course I could use the near points function to just look for points nearby coming through this slot here. But there's an easier way, which requires less computation, which is just using the endpoints function, which will return the total number of points coming in through a given geostream, and this is geostream number 1. Let's call this total PTS for the total number of points, that is the oscillators. Also, what I want to create is a float array called dists for distances. That's the array we're going to use to store the individual distances to each oscillator, like this. And I'll create a float value called maxd for max distance and initialize it to 0. And I would like to use this float variable to find out which of these oscillators is furthest away and how far it is away from my current point. So now what I'm going to do is I will create a for loop, and this for loop will run over all the points coming in through a second input slot, so that's total PTS. And for each of those points coming in through this geostream here, I would like to get their position first. Let's use a vector called npos and use the point function to access their position value. Next, I'm going to calculate the distance of my currently active point on the grid towards that point that we just found here. Let's use a variable called dist and use the distance function to calculate the distance from my currently active point position to the position of the oscillator that we just found. Next, let's put this value into our dists array here with the help of a push function. So we're going to push into our array called dists the value of dist. We just added this value to this array, basically. Finally, let's check if the distance we just calculated is bigger than our max distance value that we already have, and if so, this distance should be the new max distance value, to iteratively find the maximum distance that my currently active grid point has to any of those oscillators. So we check if our dist value is bigger than our max d value, and if it is so, my max d will be set to my current dist value, like so. Fingers crossed, let's check this. Okay, no errors this far. Let's save this. Next, after we've done all these calculations, we finally need to store our dists array onto our grid points, and also we'd like to store our max d value onto our grid points. Let's highlight this and head to the geo spreadsheet to check. Okay, we have an array full of distances here, and we have our maximum distance in this array stored here. Next, what I'd like to do is find out the global max d, so the overall maximum distance that any of my grid points has to any of the oscillator points. And I will do that just to be able to model a fall-off, because when I have a wave traveling in water or in any medium, it will get damped, so it'll get weaker. So what I'm going to do is use an attrib promote, and I'd like to promote an attribute called maxd from point to a detail. And I'd like to use the maximum promotion method and wire this up here, highlight this, and what this will do. On the one hand, it'll delete the maxd attribute here, which is fine, we don't need that anymore. However, it'll create a new attribute, a detail attribute, just a single value, which will be equal to the maximum value of all maxds that we previously stored on the point. So this is the overall global maximum of our maxd. So the furthest distance that any of my grid points is away from any of the oscillator points. Now what I finally want to do is calculate my individual sine waves and add them together to form our interference pattern. So let's do that with another point triangle, which we'll wire up here. The first thing I'd like to do is create a slider to be able to dial in the frequency of my oscillators. So let's create a float value, call it freq for frequency. And let's create a float slider. Create the interface element, and we can see we have a frequency slider here. Let's set it to maybe 55. Next we will load our array, which we stored as a point attribute, which stores all the distances to the oscillators. So a float array called dists, just like this. Also, let's load our global maxd attribute to model a falloff later. I'm going to use the detail function to access it. Like so. Let's check. No errors so far. And finally, I'd like to create a float. Let's call it amp for amplitude. Set it to 0, and I will use this float to sum up the individual amplitudes coming from each individual wavefront from each individual oscillator. So to sum up those wavefronts and to calculate them, we're going to need a for each loop. And within this for each loop, we'll go through all the entries in the dists array. Let's create a variable called dist. And for each loop, we will load one of the values from the array dists into this variable here. So the formula to calculate each wavefront is pretty simple. We just take the sine of our current distance times the frequency, and we add this to our amp value to sum up all these individual wavefronts. Just as a test, let's use this amp value to displace our point position along the y-axis. So our current point position equals our current point position plus a vector that will quickly build. It's 0 on the x, amp on the y, and 0 on the z-axis. Fingers crossed, let's see. And we see this is pretty wild what we're seeing. Yes, on the one hand, we are seeing some sort of interference pattern. On the other hand, this is extreme. And that is because we have not taken into account the damping of our waves yet. So yes, of course, what we could do, we could scale each individual wave. So if we put a multiplier down here, we can see those waves behave a bit more civilized. However, they don't have a fall-off. They just keep their strength. And in order to drive this fall-off, let's create another variable. Let's call it strength for now. And to calculate the strength, that is the individual amplitude of each individual wavefront coming to this point, I will use a fit function, and I will fit the distance between my currently active point and each individual oscillator point. So dist, I will fit that to be between 1 and 0, and I expect my distance to be between 0, so when an individual grid point is directly at the same position as an oscillator point, and max d, which is the overall maximum distance that any given grid point can have to an oscillator point. So I will use this value that we just calculated, strength, and use it instead of our constant multiplier. And of course, this needs a semicolon. Still a bit too big. So what I'd like to do is do two things. On the one hand, scale back our maximum distance to 1/4. So we have a stronger fall-off. The fall-off does not protrude as far. And on the other hand, I'd like to reintroduce my manual factor with which I can dial in how far those points will be displaced. And in this case, let's create a float slider again. Call it displacement. Create the interface. And now I can comfortably dial in how fast those points will be displaced here. So that's a really quick setup to generate interference patterns. Of course, you could extend this now. And what comes to mind here would be individual frequencies for the oscillator points, or individual damping, maybe a phase offset, stuff like that. So I'm looking forward to see what kind of extensions you guys create to this technique. As always, we're happy to see your artwork, so please keep sharing. As always, a very, very special thank you goes out to our Patreons that keep supporting us, especially Mohammed Al-Abri, Chris Hebert, Nick, Bachman, Johan Bakshi, John Koons, and Joseph Howerton. Thanks, guys. Hope you had fun with this. And as always, it's cheers and goodbye, and see you in 2 weeks.